So we've introduced some ideas of a low-level microcode multi-cycle data path construction, and this is going to be our first guess. Okay, we're going to put all of the bits together that we know we need. And if you're not sure what any of these things are, you could go back and have a look at some of the other videos of putting together the bits and pieces that make a data path. But really simply, we've got memory, which accesses data, right? And again, because it's von Neumann, your instructions and your data both go there. We've got a program counter that's going to count through which instruction we're looking at. We've got an instruction register that's going to store the information of what to do at each step, right? We've got the register file, which for our really simple assembly language is only going to be two registers, register 0 and 1. And then we've got the ALU, which is going to do the math. It's going to add or subtract. And it's also going to do our program counter update if we have to take a conditional branch. It says no branching yet, but I believe this can do branching. There may have to be some decisions to be made. We've also got this condition code register, which is going to tell us something about the ALU, right? If the ALU result was 0, then we take the branch. If it wasn't, then we don't. This is the kind of thing. And then we got this sort of magic box here called the control unit, which is really what we're unpacking when we're building out the microcode stuff, and we'll see what goes in there later. So if I started with the idea of put down the boxes that do the things and wire them up so that everything can talk to everything else, this is more or less what you would get. And it works okay, but there are definitely some constraints to it, right? There's some things that as we get more complicated, we might want to do a slightly different thing. So how do we build that out? Well, first thing I want to do is take a step back and introduce a notation that we're going to use called register transfer notation. This is going to give us an idea of where we're going to move things and make it easy to sort of specify. When we put something in square brackets, that just means the contents of. So we're putting the contents of R0 into R1, and we're copying it. We're not moving it. We're not getting rid of it when it's in R0. We're copying it. And to get really, really specific, what this means is when we're looking at the clock cycle for a single cycle of a machine like this, we're going to first, before the rising edge, we're going to set up the control points to make this register transfer happen. And then when the clock edge rises, the registers are going to activate, this multiplexer is going to do the thing, and data will move from R0 into R1. That's what we mean when we put this kind of figure down. So you'll see this come back and forth again, and if you're ever confused, you can come back here and have a look. So here's the machine that we built out. Sorry, I'm sort of blocking the condition code register there. Let's look at the register transfer notation to do something like a fetch. This is the first part of any instruction. We have to get the instruction from memory. So what do we have to do? Well, first, we have to move the program counter into the memory address register. Because remember, we've isolated memory. We don't have a direct line from the program counter to memory. We have to copy it to the memory address register so that memory can do its thing. That's one clock cycle. Then we're going to increment the program counter because we want to next instruction, look at the next instruction. So that's PC plus 1. Again, that takes a clock cycle. And we'll see there's some optimizations we can do a little later. Then we're going to have the memory do its job, which is the memory receives an address from the memory address register, and then it does whatever it's going to do, load or store or whatever, into the memory buffer register. In this case, we're going to load. So the memory address register addresses the memory, and the result goes into the memory buffer register. And then finally, from the memory buffer register, we go into the instruction register. This is a 4-step process that we need to do to allow us to grab an instruction from memory and put it into the instruction register where it can be used to decide what to do next. If you've watched the videos on building a single cycle machine, this looks way more complicated than it should be. And it's true, it's much more complicated than the single cycle machine. But when we get into the sort of optimizations that you can do and the multi-cycle nature of it, you'll see why this is another approach. It's not necessarily a better or worse approach, but it's just a different approach to understanding the control logic required to build out one of these machines. Once we've fetched an instruction, the next thing to do is to execute that instruction. And it's important to note that the fetch has to be the same for every instruction, because until this fetch is completed, we don't know what instruction we're executing, right? And we can't make any decisions about, oh, I do it differently for a load or an add, because we don't know if it's a load or an add. So the fetch must be the same for every instruction. The execute can be different. And so here's an example. If we're going to load an address into register 0, this is the process we have to do. We're going to take that address from the instruction register, and we're going to put it into the memory address register. Okay, that's one clock cycle, that transfer. Then memory is going to do its thing again. And this is where we get some advantages, because if memory, the only thing it has to do is MAR to memory to MBR, then we can optimize that process. We could speed it up. If we're doing things differently with memory, then we have to make it do things like every time it does something different, we have to make that process faster or slower. So having it consistent means we can make it efficient. So we do memory does its thing, and then from the memory buffer register, we're going to put that into register 0. And you can see there's another line right here, right? Memory buffer register can write directly into the register file, which is where register 0 is. And so this is the full 8 clock cycle process to do a load instruction. The first 4 clock cycles are going to do our fetch, and then the next 4 clock cycles are going to do our execute. And each of those operations can be incredibly fast because it's doing only one thing, right? Our single cycle machine that we built in a different video, the clock cycle is going to be much longer because it has to do a whole bunch of stuff in a clock cycle. Control is easier, but the result is a faster clock cycle and more efficient operation. So this is our basic machine. Next step is to take this and recognize that we can maybe do better. We can build some efficiencies, right? This has wires sort of everywhere, and we want everything to be able to talk to everything. As we try to implement branches, as we try to implement other things in here, we're going to notice that we have more wires going in more directions. And so instead, we're going to take a step back and introduce a new idea called a bus. A bus is just a set of wires that connects everything to everything. And then you're going to have switches that allow some items to be put onto the bus and other items to be read from the bus. The control logic has to decide what's going to go on the bus and what isn't. But the idea is if we're sort of moving towards connecting everything to everything, then why don't we just connect everything to everything and allow anything to be put anywhere? This gives us a lot more flexibility with our machine. And the other thing it does, again, with this idea of microcode, is to be able to come back after we've built the machine and change the way it operates. If we don't have everything connected to everything, then if later we decide we want to have the ALU go straight to the instruction register for some reason, we can't because there's no wires there. But if everything is connected to everything via a bus, we can then go back and change the firmware, the microcode, right, to allow different kind of operations that we might not have thought of when we built the machine from scratch. This is another innovation that starts to come in when we have a separation between the people who build the machine and the people who program the machine. You want to make it so that other people can write code for it and make it as easy as possible. So here is the process for taking that generic everything connected to everything machine and turning it into a bus machine. Here are the two machines. And again, I sort of closed it off. Maybe I'll just turn that off. There we go. Here are the two machines. And you can see on the left, we have the machine that we've built out where everything's sort of connected to everything. And all we're doing first, in order to make this a bus, is stacking everything sort of in the same angle. And it's the same process. So the memory is still isolated. The program counter is here. Now, one thing we're going to be able to do with a bus architecture is allow the ALU to increment the program counter rather than having a separate incrementer. So we've lost an incrementer. Isn't that interesting? And then we've got the same register file, the same ALU. It's all the same parts. We've just shifted it around a little bit. And now it looks like this. All right, let me bring my face back in again. This is the beginning of a multi-bus machine. And what we're going to do is we're going to have connections from everything to the ALU, and then from the ALU to everything else. This kind of architecture is sort of ALU first. It's ALU-centric, recognizing that this is the mathematical heart of the machine, and so we want everything to be able to run to it and everything to be able to receive from it. Now, we're going to need to do a little bit of extra stuff because if we're going to have these wires connected to everything, we need some ways to turn them on and off, and then we need some way to choose which ones are turned on and which ones are turned off. And so we'll build out the control logic for the 3-bus machine, that's this machine, in the next video.